My name is Paul Ricketts. I'm with the University of Utah. We're talking to Luca Visinelli tonight. He is an ex-grad student for the University of Utah. I think you graduated in 2011, right?
Mm-hmm. December 2011.
Okay, so yeah. So he got his master's and doctorate there?
Yeah.
Cool. Let's see, you moved around a little bit between now and then to different universities doing teaching and research and stuff like that in a couple different fields I saw. So but you just barely started a new position in Italy? Where's the university now?
I'm about to start in a few months in near Rome. It's called Frascati. That's where the national laboratories are.
Okay.
Like the headquarters of the national laboratories.
Sorry,
this is a network in Italy that coordinates different experiments. The network is spread throughout the whole of Italy. The headquarters is in Frascati. That's where they have a bunch of experiments on Axion going on, something that might go on in the future, among with other experiments of other types are ongoing. I'll be moving there soon.
Cool.
As soon as I can go to a laboratory.
And so you'll be actually working in a laboratory and not at a university position, like a professorship, right?
It's a Marie Curie, so it's a 3-year postdoc.
Ah, gotcha.
Yeah.
Cool. Well, that sounds exciting.
I'll be working as a theoretician. That's my background. That's what I did in Salt Lake City as well, where my background as a PhD student is. But I'll be mostly trying to interact with experimentalists and observations as well. So I have a lot going on both the direct detection experimental side and on the observation and radio astronomy side.
Okay, that's cool. So you're going to be really busy. So it's good we caught you now, right?
Well, no, now I'm not busy. Here it's 2 a.m. My schedule is free now.
That's good.
So it's a good time to be
doing
live
it.
on.
Yeah. Okay, great. Can you tell us a little bit about how you got to where you are? I know you got your bachelor's in Italy. Was that where you? Okay, and then you moved to the U.S. So can you tell me what made you become interested in Axion physics and just maybe physics in general? This is kind of more of a question for maybe incoming students and students that are trying to decide where they want to go. So can you just give us an idea of what you did to get where you are and what drew you to that field?
Yeah, absolutely. So I was always interested in how things work, what's underneath anything you see, what's the prime constituent of anything we observe, and what's the cause for anything we feel and we perceive. So I was also interested in science. I liked animals, in particular ancient animals. I wanted to be a paleontologist before the first Jurassic Park came out. And when the first Jurassic Park came out, I was astonished. I thought, okay, yeah, this is a movie about what I want to do. Fantastic. So I wanted to study dinosaurs. In order to do that, you need to be a biologist, see? But then I went to high school with that idea. And I discovered that in order to do biology, you need to be to know chemistry. Okay? But in order to do chemistry properly, you need to study physics. So I said, okay, let's go into physics. Let's see how these things go first. And I just got involved into that. I had a very good physics teacher in high school as well. So this combination of interest and good physics teacher brought me into university to choose the physics in the university after that. So yeah, bachelor in Italy is 3+2. So it's basically 3 years of bachelor only, because we have 5 years of high school. And then we have 2 more years for a master, which is not recognized internationally as a master. So I had to do it in youth as well. But I also did my last year of master in Italy in Salt Lake City. So of 5 years total in Italy, I just spent 4 of them there. And the last year, officially I was a student in the University of Bologna, where I'm from. But in practice, I was already in Salt Lake City because, I moved there to work with Paolo Gondolo, who's one of the personnel in physics, in the physics department. And I started to work with him on neutrinos. So my Italian master thesis is on neutrinos.
Okay. And
then I finished that in 2007, and then I started my PhD program in the University of Utah. So it helped me to get into the PhD program because I was visiting already. I had a clue of the American system. It was easier for me to go with the enrolling procedure.
Right.
Because I was there physically when I was applying.
So then, after you got your master's, what did you get into that led you into axions during your graduate work?
Paolo was interested in that. So, okay, let's see. The story of axions goes. Okay, let's try to focus on what these particles are. Well, they are a possible constituent of dark matter. When I started my PhD, another popular candidate was WIM, weakly interacting massive particles. It was thought to be the dark matter particle associated to supersymmetry, so associated to a kind of physics that was expected and hoped to be seen at the LHC, at CERN. So when I started my PhD in 2007, 2008, CERN was about to start. The LHC was about to start. We didn't have data yet. We now know that, they have not found yet what they were looking for, even if the research is still ongoing. But basically, less and less people were thinking about axions back then. It was just a bunch of people that were interested in these particles 10 years ago. The community moved to this particle relatively recently, in the last 5 to 6 years, basically after the supersymmetry was not found in LHC. So this doesn't mean that supersymmetry doesn't exist. It could be behind the corner, we have not seen yet, but people are thinking about other types of dark matter now. So basically, we had shift from 10 years ago, in which up to 10 years ago, in which WIM meant dark matter particle. It was a sort of one-to-one connection, to nowadays, in which people are considering way more exotic scenarios seriously. The point is that the Axion is not that exotic because it's a particle that was firstly postulated in the standard model in order to solve a specific problem of the standard model.
Right. So let's go back just a little bit because some people may not have even known what like the standard model is. Let's go back a little bit. I think it was like when it first started in the 40s and 50s and 60s when people were starting to look at particles. Like initially they, of course, had like the proton and the electron, and through studying stuff they came up with, they found neutrons. Through the even more studying, like through cloud chambers and stuff, they started to discover even other things like positrons. They started to find out there were neutrinos, and then all of these particles started getting people to think about what other stuff is out there. So you had people like, do you remember who like the main people that were taking that? I think it was who were the main scientists back then, like that helped us start it? Do you remember some of the names that started thinking about the standard model?
What is it? The standard model has been built by a lot of different trials and error throughout decades.
And so
for example, the 30s, the neutrino was postulated. It was then discovered much later. Basically, the idea, the guidelines are energy conservation. Mm-hmm. You need to have some guidelines.
Right.
Do some good science and have some clues where to look at. For example, energy conservation in processes that involve the neutron and the electron lead to postulate the existence of the neutrino.
Right.
Because you see a non-conservation if you neglect the neutrino in like proton, neutron, electron interaction vertex. So people knew about the proton, the neutron, and the electron in the early 30s because of the atomic experiments.
Right.
And because of the energy conservation, they were led into postulating the neutrino. And then, they had the first block of what's now called the standard model. So the standard model can be roughly divided into, basically the standard model is a model of particle physics that explains matter and their interactions.
Right. So you it kind of builds on like their properties, so their mass, their spin, their charge, how like they come together, when they interact, what other particles come out, what kind of changes in masses that they have between them, just basically how everything kind of fits together in a big puzzle, and you're just kind of splitting the pieces apart and kind of seeing which ones are similar here, which ones are similar here, how they might interact in this way, or if they do interact in any way at all. So like the neutrino, you were talking about that. That doesn't really interact very much. So before you mentioned the WIMP, which is a weakly interacting massive particle. So like a neutrino would be like a weakly interacting not very massive particle, kind of.
Yeah.
Exactly. Go ahead.
So every word that we say in science has to be precise. So when you say weakly, we mean exactly one thing. It means weak interaction. It means that it's an interaction that's mediated by some carriers. In the standard model, we have basically four different. We know that there are 4 types of forces in nature, and the standard model captures 3 of them, which are the electromagnetic, which is responsible for most of the events we see. The strong force and the weak force. The strong force is mediated by gluons, and it's responsible for holding together the quarks, which are the ultimate constituents of a nucleus, so of atomic nuclei together, and it holds together proton and neutrons. Whereas the weak interaction is responsible for example, for nuclear decay. And it's also responsible for the force that's felt by the neutrino or by a hypothetical wind.
Right.
There is also a fourth force, gravity, like the elephant in the room. The big question in physics that's been basically that kept always lingering around in the last century has been how do you connect gravity with the standard model, so with a quantization of the interactions.
Right.
So how do you blend these two theories?
Yeah, and that's been a very difficult question for a lot of people.
Yeah.
Yeah, it's there's very few even decent theories to bring those together. There's some
have a theory that does that yet.
Right. So yeah, that's the standard model. Like he said, it's kind of like the governing model to explain how particles interact and their properties within them. And so you work on what's called an axion, and the axion is part of the standard model, correct? It's theoretically brought about by some of the standard model. Is that a correct way of saying it?
I wouldn't say that's part of the standard model. Well, it has not been found yet.
Right.
We don't know if it exists. It's related to a problem of the standard model. That's always related to symmetry. So remember that we have to be led by symmetry. In this case,
and can you kind of explain symmetry really quick, just because most people probably aren't aware of what that is?
Well, there are different types of symmetry in nature. For example, I have a right and the left hand. Mm-hmm. They are symmetric by the parity. I can change one into the other. If I change one of the axes from the if I look at myself in the mirror, left become right, and vice versa. This is called parity, symmetry. We also have different other types of symmetry in nature, like time symmetry. Basically, what does physics do if we reverse the arrow of time? And charge symmetry. So what does physics do if we change the charge, for example, of electrons and protons? If we make electron positively charged and protons negatively charged. It is believed that the product of all these three symmetries, charge, parity, time, CPT, is conserved. It means that if I change charge, parity, and time in a physical system, I get the same physical system behavior. However, we can break each of these pieces separately, or combination of them. So I can have a interaction that breaks the charge, an interaction that breaks parity, or an interaction that breaks charge and parity, so that CPT is still preserved. And this type of interaction that break CP, charge parity, are extremely valuable in physics, because we know that they exist and they occurred. Why? Because we are here. So if you believe that the universe started with equal amount of matter and antimatter, So with what we're made and the correspondent antimatter, well, there is clearly a predominance of matter, of antimatter in the universe. So one big question is why this happens. And the key ingredient that you need in order to explain this is breaking of CP.
So that's the charge parity.
Yeah.
So we have a question, just a quick question I can answer. So Susie asks, charge part-time. So when he says charge, he means like the charge of a particle, like an electron is positively charged, a proton is or positively charged, neutrons are neutrally charged, so there's no charge. Time meaning like you're moving forward or backwards in time. So as he suggested, if you were to have a system of two interacting particles and they interacted forward in time, they should have the same reaction if you move that reverse or the opposite reaction if you going backwards in time. Correct?
Yeah, exactly.
And
so
then,
if I have a particle that's basically moving toward left with a plus charge, and the arrow of time is positive, is the same as a particle that moves to the right with negative charge, moving backward in time.
right.
So all of these can be expressed precisely in mathematical terms within what's called quantum field theory. So quantum field theory is the branch, the tools that allow us to study how these particles interact with each other. And it's basically usually one of the most advanced classes in a master in physics. So basically what we're talking is quite high level in terms of mathematics and concept. Still, super interesting. That's how things are.
It's fun to know that it exists, even if you don't want to dive into the mathematics.
Well, it's good to know that there are strong mathematical backgrounds to what we're saying,
yeah,
even if you don't touch them.
Right.
And so they're there, and people can get interested, can get into that.
Yeah.
Yeah. That's what theoretical physics does. It basically builds block to get there.
Right.
Because you need tools in math and tools in physics to get to quantum field theory, which is basically
right.
Together with general relativity, so the study of gravity around massive objects. This is basically what's most advanced a course in physics can offer you.
Yeah. Okay, so now that we kind of have the standard model, we're to the point where we can talk about where axions kind of had to come up. And you mentioned CP, charge parity, and axions come into play there because they help to explain, they help to keep it unviolated. So if you have axions, they help to explain that it is not being violated by something. Do you want to talk about that briefly?
You have the possibility, there are different possibilities to break this CP charge parity symmetry within the standard model. One of them comes from the strong sector of the standard model, which means the sector that studied the strong force, which I briefly mentioned before, the force that holds together protons and neutrons in a nucleus.
And they're mediated by what's called a gluon. So
exactly.
If anybody have ever heard that, you kind of get an idea. So there's a particle called the gluon that I guess regulates the field between quarks and holds them together. And so inside a proton, you have three quarks that are held together by gluons, and then that collectively creates a proton. There's something interesting with that, though. If you look at the mass of the proton, the mass of only each of the quarks don't explain the entire mass of the proton. So the actual mass of the proton, a fair amount of it comes from the force that actually holds them together with the gluons, right?
Yeah.
Yeah. And so...
in E equal mc squared, well, that's not all of the story.
Yeah, it's not.
Momentum is also part of the energy.
Correct.
So that's what enters into your answer.
Right.
Yeah.
Okay. So that's when he talks about the strong force. That's what he's talking about there. The weak force, that's governed by which particles?
Well, there are bosons, the Z and W boson.
Z and W boson. That's right.
So the Z boson can be thought of a massive photon.
Right.
So
And
the photon has mass 0.
right.
And is without any charge. It's neutral. Same is for the D boson. It's neutral, but it has a very large mass.
Right.
Mass means screening. It means that the force can only go for a finite distance.
Right.
So this is a short distance force.
Yeah, and these particles only exist for a very short amount of time, also, right?
Yeah, because they decay into lighter particles.
Right.
So they can be. It's called basically virtual particles. They're called virtual particles when they mediate the interaction. If you make them real, then they decay into lighter particles.
Yeah. Okay, so...
Yeah. Same for the double bosons, which are charged.
Right. Okay, so I threw that in there just so people understand when you're talking about the strong force and the weak force and charge parity, they kind of have an idea of where that came from. Okay, so let's keep going.
Yeah, so well, there is a lot. We're basically going through everything in the standard model, so it takes time.
Yeah, well, I think it's important to figure out where it came from, and it's not just something that kind of like, physicists thought of something, and now there it exists.
We can pull out a table for this, but in the meantime, so in the standard model, you have the strong sector. Within the strong sector, you can expect from the mathematics to have a violation of CP. You go in the laboratory and you find that there is no violation of CP from that sector. So what's going on? There's something that's not working. So we expect some violation of CP from the strong sector, but we don't see its effect. That's when where the axiom comes into help, basically, because it helps to relax the assumptions in the standard model, and it helps to explain why we don't have a violation of CP from the strong sector of the standard model. So this particle is needed for this purpose, for fixing this mystery that's plaguing the standard model.
Okay, I have a question for you then. So, if the axion doesn't exist and CP violation does exist, what does that do to the standard model? What does that cause physicists to do?
Well, there are other. The axion is basically the easiest solution, if you want. Other solutions could be. It just happens that the parameter that in the standard model regulates CP violation in the standard model is extremely small and fine-tuned. So we have to explain why. You have to build a theory that goes beyond the standard model and that builds, so gets this piece of mathematics in the strong sector of the standard model with such a low value of CP violating term. So this would also require new physics. Unless we accept that this parameter is extremely small just by chance. There is also another the simpler explanation would be that one of the quarks, like the up quark, is massless. We now know that this is not true. If one of the quarks were massless, then everything would be fine.
Right. But it's not. It has mass.
And if I can share, it has mass, so yeah, axions. It has mass, so axions. Sorry. Let me share screen with you.
Okay.
Is that fine? Oh, here.
I'm not. Oh, there it goes.
Okay, so this is the usual chart that we see when we talk about the standard model. So we have 3 pillars here, in which in each pillar we have 2 quarks, up and down. Up is positively charged, down is negatively charged, with fractional charge, 2/3 for the up and minus 1/3 for the down. And we also have 2 leptons. One is the electron and one is the neutrino, which in the standard model is massless. And this pattern here is repeated 3 times. And then, so with each generation being more massive than the previous one. So we also have, on top of up and down quark, charm and strange, and top and bottom. And they come with their different flavor leptons. On top of that, we also have the gluon that we discussed. That's the mediator of the strong force. The photon, which is the mediator of the electromagnetism. Z and W bosons. All 3 together, photon, Z and W boson, make up the electroweak force. And then we have the Higgs boson that gives mass to everything and was discovered in 2012 at LHC. So the Higgs boson, this particle, was basically the main motivation for building the LHC, besides looking for supersymmetry.
Right.
So, yeah, it's fascinating. This is the standard model. It came up in patches, as I said, so that someone one day said, okay, this is how nature works. This come out of decades of trial and error. Still in the 60s, people were puzzled to understand the manifestation of the quarks. So basically that's how science works. It's the joint effort of hundreds and thousands of people in a community that have some common goal, and they have some common way of proceeding,
right,
with a scientific method, and they achieve that's what they achieve. They achieve the better understanding of nature. So the important thing to understand is this is not the end, but the beginning. In the sense, there are cracks in this standard model.
Yeah.
There are things that we don't understand. For example, the axion, or why we have a non-violation of the CP from the strong force in the strong sector of the standard model. Another thing that's super important is that we know that neutrinos have masses because they can oscillate, so they can turn one into the other. So we have a lower limit on the neutrino masses. Why? This is not explained in the standard model, and means that this also means that there is new physics.
Yep.
Okay. So.
Okay.
Right. About this.
Okay, so we have a better understanding of why axions came out of the world. So let's talk about like what you do with them, like what you're researching, what your research focuses on with them. And I noticed you have a couple, well, actually several different aspects of axions that you have studied and their applications. So let's just go through some of those real quick, and well, not too quick.
Yeah. First of all, axions can be the dark matter. So let me pull out again some slides I had here. So let me share screen again. Okay, so now we come to cosmology. You should see my screen now. This is from
yes.
Okay, very good. This is from a talk I gave last month, I think. Yeah, in Shanghai. It's very easy to travel now remotely. This pie chart is what we think that the universe is made of today, as of today. So these are other cracks in the standard model. We have to explain most of what we don't see in the universe. So all of the standard model make up the ordinary matter here, which is only 5% of the energy content of the universe. We need dark matter. We need dark matter to form galaxies. So this goes into the other branch of physics that I like. So we step away from particle physics and we go into astrophysics and cosmology. We see galaxies around. We see galaxies with telescopes. They come in structures. We can simulate how they form. But in order to do that, we need this component which behaves, behaves as a matter component, but it's dark in the sense that it's not strongly interacting with light. So the coupling of this particle, dark matter, with light is extremely feeble. The axion can be this component here. So this is why this particle is so interesting, because it provides basically the explanation for two different problems. Dark matter problem, we observe the dark matter, we don't know what it is, and this problem within the standard model, the strong sector of the standard model.
So,
well, yeah. Please.
You'll probably get to this, but in what manner does axions fit dark matter? Like, is it? You mentioned that it's a weakly. It acts on the weak force.
So.
And is it a very massive particle, or is it very light? It's
extremely.
And it doesn't interact with anything very well, correct?
It doesn't interact at all. Yeah, it's the coupling with other like photons or other particles is extremely suppressed. I don't want to scare anyone with equations. I just want to show what the idea is. Basically, as time proceeds, the axion can be thought of as a field that is set in motion at some point, in the cosmology of the. So at some point in its history, basically when its mass is of the same order as the expansion rate of the universe. From this moment on, the axion fields start to oscillate. So it behaves like a pendulum.
And when you say oscillates, can you kind of give a description of like what you mean by a field oscillating?
Sure, these are like excitations over a background field. So you need to think like a rubber wire that moves. This is the same as what this particle does.
So instead of like a particle moving back and forth like a weight at the end of a pendulum, you kind of have a three-dimensional sheet of energy, and that energy is wiggling a little bit?
Yeah.
Okay.
Yeah. You have this sheet that makes up your background, and the axion is it's called the quantum, is the excitation of this background. And it's a sort of oscillation over this background. Since it's an oscillation, it's how to say, periodic.
Uh-huh.
And so it returns after some time to its previous position, so it performs oscillation.
Right. So
and,
one quick thing I think some people may not understand about fields themselves. So kind of like in a very general sense, when he talks about an axion field, we have things like a gravitational field, which is this field of, I guess, an energy field is what you can call it, that extends throughout the universe. And in terms of particles, you have this same, it's a similar type of idea, where you have like the strong field is a field that permeates throughout the universe, and particles are small little bumps in those fields. Is that?
Yeah, well, you have this wave-particle duality. So this is the foundation of quantum mechanics. We're getting into this. Any particle can be seen both as a wave and as a particle, as a corpuscle.
Right.
For example, light. Light has usually we see light as a wave. We experience it because we experience its diffraction, its reflection. But in some experiments, you can build up an experiment in which one quantum of light, which is basically the smallest wave packet that you can think of, or the particle that's associated with the electromagnetic interaction, hits an electron. An electron itself, we usually think of it as a particle, like it's this particle that surrounds the nucleus and make up the atom. Still, we can build up an experiment. We can do the opposite. We build up an experiment in which the electron has wave properties. It diffracts. It behaves as a wave. So, in physics, there is this wave-particle duality. Every particle expresses some wave phenomena in some conditions. Every wave expresses a particle phenomena in some conditions. This is the same for the axion. We have an axion field, on top of which the particles are called the quanta, and we can treat them as individual particles themselves. I hope this helps.
Yeah, no, that's so. I wanted to go there because if you start talking about fields, then it might confuse some people. Is like because because like a long time ago when I was getting into physics, I was like, I don't know what the hell a field is when you say that, and so it's better just to throw it in there to help, just understand what you're referring to, I guess, is the easiest way to say it. So
a field is basically quantity that's associated to each point of space and time. You associate one value of the quantity that you're studying.
Right.
For example, for the axion, you say that the axion has one value for its energy density, for example, in each point of space and time.
Right.
So you have basically mapped a field into your space-time in this way.
Perfect. I think that is understandable. Okay, so let's go back to your slides and talk about those again.
So basically, you usually use when you think about dark matter, like you think of dark matter in terms of massive particles, like the WIMP that I mentioned earlier.
Right.
It was the archetype of dark matter up to a few years ago, before the community shift to be more creative. I think this is fair.
Yeah.
So the archetype of dark matter was the WIMP. The WIMP is so massive that it's basically the energy. It behaves as a particle. Its energy is stored in its rest mass, which means that we have some volume of space. The energy that we perceive as dark matter is given by the mass of the WIMP per unit volume. For the Axion, it's different. It's not only the mass, the rest mass that gives this particle the energy, but it's the oscillations of the field about it, that behave as dark matter. So it's two different phenomena that give rise to the same perception of dark matter field.
Okay.
And this is basically ultimately due to the fact that they're so different in mass. Like the WIMP is expected to be hundreds of protons in mass. We don't know. We don't know even if this particle exists. It depends hundreds, thousands of protons.
Right.
It could be a fraction of an electron. Well, not a WIMP, but dark matter could be ranging within the fraction of the electron.
Right.
So that from last week that we had this xenon success in the KV. KV is 1/500 the mass of the electron. Mm-hmm. So we need a particle with that mass. And then we have the extremely light particles like the Axion that can still serve as the dark matter particle. By extremely light, I mean a millionth of an electron volt.
Right. So very, very small.
Yeah.
Okay. So
when I say that the mass is in the electron volt, I mean E equal mc squared.
Right.
So E, the energy is measured in electron volt, and you convert the mass in electron volt over c squared. But C is usually set as 1, so don't say that.
Right. So it's the rest mass of a electron is.
The rest mass of the electron is around half a mega electron volt.
Right.
So the electron volt is referred to the kinetic energy. But a particle of charge 1
mm-hmm.
with the experience when you have a field of 1 volt, a difference of 1 volt.
Right.
So 1 electron volt means that 1 electron would be accelerated, would acquire this amount of energy in 1 volt of potential difference.
Perfect. Okay.
Yes. This is the concept of the electron volt. Since E equals mc squared, we can translate a concept of energy into a concept of mass.
Right. Okay. So, when it comes to axions as a dark matter candidate, what are some of the properties that it has to have in order for it to fit that description? Does that make sense? Or
Yeah. Well, we know that. So, in the community, it's good to distinguish between the QCD axion, where QCD is an acronym for a strong interaction, basically.
quantum chromodynamics, right?
Exactly, quantum chromodynamics. So the QCD axion is the axion associated to the solution of the problem of the stellar model that we discussed. So it's the classical solution that we discussed during the slide. You can be more creative and think of cousins of these particles, which are called axion-like particles, or just axions for short.
So would that be something similar to like how quarks come in different flavors? So there'd be like different flavors of a axion?
You can build models with more than one axion.
Mm-hmm.
Yeah. In which one of them is the QCD axion, and there are also cousins, like it happens in the stellar model. When you do this, you need to have in mind some problems that you want to address when you want to complicate the scenario. It's because you want to address more than one problem, or because you can do better in addressing, for example, dark matter problem. But for the dark matter problem, the QCD axion suffice at the lowest level, let's say, the lowest levels of complexity.
Mm-hmm.
The properties, well, there are bounds on the mass of this particle, because if this particle becomes too massive, so if the axion becomes too massive, then there are problems with the cooling of stars. So you have to think of everything when you introduce a new particle.
Yeah.
But this is why I said the axion has a mass of a millionth of an electron volt, but not, for example, an electron volt, one electron volt. Because if it were 1 electron volt in mass, it would give a channel in which stars and white dwarf would cool off. And this doesn't match what we see.
Right. So you have to build your models to actually match what you are seeing, instead of the other way around, where you build what you're seeing and just throw something in there and say it exists, right? So that's like the part of science that is the.
You can say that we have a theory, and you want to see how strong the theory is.
Right.
So this theory of the axion, does it survive other clues, or can we kill it and think of something else? This is also very sane.
Yeah.
If you can say, okay, this is not a good solution for the dark matter problem or for the strong CP problem, let's prove it and move to something else. Well, for example, you cannot have an axion which is too massive. Because of this, because of the cooling, because of astrophysics and stellar bounds.
Right.
So this is one of the properties. Well, there are other properties that are related to how it is formed in the early universe. And this is where we get a bit technical. So you need to be in the right cosmological setup. Not all of the cosmologies, not all of the histories of the universe work.
Right.
So you can look for ways in which you can look for caveats always, which is what I did with Paolo. You can look for ways in which you can constrain your theory. So basically, in the future, experiments that can probe the cosmology that you need can tell you whether the action is viable or not.
Right.
Yeah. So this is one of the scenarios. So this is quite rather large, I would still say. This is why people are taking this particle seriously.
Yeah, that's it's interesting that it can fit so many things. I think that gives it a lot of leeway in further searching for it. I think what we can do is you're okay on time still, Luca?
You can go on.
Okay. Because I want to get to a couple of the other things that you've looked into with axions, but so for the dark matter aspect of it, what's the chance that we would be able to see it? What kind of setups, or like how would we be able to detect it, and kind of like where would it exist in our around our galaxies, or is it like spread out like through the galaxy homogeneously? Is it kind of clumped up in different places? Could you explain a little bit about those ideas?
Yeah. So you're informed about what I'm doing. Yeah?
I told you I was going to do that. I can't go into this blind.
Very good, very good. Yeah. Let's go to my slides. So, which you should see now, I think.
Yeah, they're up.
I want to show this drawing here. Where is it? Here, perfect. So, this is called parameter space. So the mass of the axion is on the x-axis. This is a mass in an electron volt. So 1 electron volt is here, to the very right of the corner of the graph. And then we go down in energy by a lot. So this is a billionth of electron volt here. Axion can be this light. And as you see, experimentalists and theoreticians have been very good at designing experiments that cover most of the parameter space. Only this ADMX cavity, which is basically field lines and bounds, have been done so far. So what are we looking here? The QCD axion is this yellow band here. So the axion can live anywhere in this region. Can have any mass from hundreds of electron volts down to billions of electron volts, and correspondingly you have the coupling with the photon. So this G A gamma tells you the strength by which the axion couples to the photon. I said that the dark matter doesn't couple much to the photon. Still, you have some coupling, and it's basically quantified by this quantity here. And since this is a straight line, you see that the more massive the axion is, the more it couples to the photon. This is why you cannot go that much high mass, because when you get too much massive, the axion couples too strongly to the photon and you screw up with observations. You basically don't match with the stellar bounds or with the laboratory bound anymore.
Right.
So in this view, the axion lives in this yellow band here, which will be covered by these experiments, which are relatively cheap, which means in the order of $1 to $10 million compared to tens of billions, which is the LHC, solely building the LHC.
Right.
And the personnel that it requires. So the number of people that's required for these type of experiments is also modest. This is why I think this is also why the community shifted to this type of experiments. We can build them, they can be financed, it's interesting, and there's plenty of room for this. So not all of the masses would do, of course. The axion can be the dark matter in a band. It depends on the cosmology, as I said, but in the setup, the cosmological setup I have in mind, they can be the dark matter between 10 to minus 5 and 10 to minus 4 electron volts. So respectively, 1 in 10,000 and 1 in 100,000 electron volts in this mass range, which would be covered in the future. So basically, order of time, 10 years, we would know.
So these ones are current. These ones are ideas to constrain the mass of the axion, and if you don't find it in those in those experiments, then that basically says that it doesn't exist in that area, and so you can kind of change. You can change your future experiments and your ideas of the physics to potentially fit a different idea of where it should be.
So the axion that solves the strong CP problem can be anywhere on this band. The axion that is the dark matter is more narrow, constrained to this to this region here.
Right. So how do they go about detecting it with those? Is it like it's not like an imager on a telescope where it takes in photons, or is it something like a gravitational wave type thing where you're looking at something like that? How would they go about actually detecting this? What is the mechanism for detection?
Yeah, you exploit this axion photon coupling. This is the weakness of this type of experiments, if you want, because they rely on the axion being the dark matter. So this solid line, for example, this solid region here, so reaches some sensitivity. Okay, it means that you can probe values of the coupling that are as small as this tip here. However, this is true only assuming that you have all of the dark matter in axions. If this is not true, this bound degrades. It scales up with the density of axions around us. If you assume that all of the axions is all of the dark matter is in axions, then these bounds apply, and the technique makes sense. The technique that they use is a cavity search. So you build a magnetic field of inside some cavity. The magnetic field is one leg of this Feynman diagram. Magnetic field is part of the electromagnetic force, which is carried by photon. So you build one of these legs of the Feynman diagram with a magnetic field. Your axion now makes up the cosmic abundance of dark matter. So it's all around us. It's provided for free by nature, and it makes up this other leg. So what you want to see is the conversion of the axions that make up the dark matter into the magnetic field to give out a pulse, which is the third leg. So what you look for is this outgoing photon. Yeah.
So magnetic fields interact with an axion to create an kind of an excess of photon that shouldn't be there with any other thing that's around it, correct?
Yeah. You need to pick up a photon of the same frequency as the mass or the energy of the axion.
And so that's kind of an idea that is known. Like, so if you see a photon of this frequency, you're pretty sure with some confidence that it came from an axion production, given that this is the experiment that was supposed to happen.
Given that you know the background, you have it under control, and given that you reach statistical significance.
Right.
So basically yes. If these people look at this type of signals, I might even have a. Let me check if I have something. Where was this? Maybe I have a plot of what this should look like. No, I don't. Not here.
That's okay.
It's okay. No, okay, but basically you would see a spike. You would see a spike in the here.
Oh.
Yes. Went up. Okay. While I look for this, is this clear? Or
yeah. I think it's clear. If anybody has any questions on this aspect of it, feel free to do it. But we do have a bunch of other questions that are related to what you can talk about already.
It was this graph.
It keeps jumping past.
Yeah, I was not expecting to talk about this, but it's okay. Right. Okay, so this is the mass of the axion. I assume it's like 3 microelectron-volt. And the power inside the cavity should see a spike, much more pronounced spike than this, at the resonance frequency, which corresponds to the axion mass. So if this is a new particle, you are resonantly converting the photons that make up the magnetic field of your cavity. And this is why the absorption, the power that is emitted into photon has a peak. Of course, this could be just statistical. You need much more significance in this. Okay. This is the same idea, in principle, as direct detection for WIMPs.
Right.
So what did they discover last week? You heard about this excess at Xenon, no?
Yes, I did. I'm not sure if anybody else has yet.
So basically, this experiment, Xenon, is actually in the laboratories of Gran Sasso, which is a mountain here in Italy. And there's this huge underground laboratory that looks for dark matter. Not for Axion dark matter, but for other types of dark matter, like WIMPs. The idea is that the incoming dark matter that make up the halo around us is made of these massive particles with mass of hundreds of protons, like a WIMP, and it strikes a nucleus of a target, leaving some energy, and you look for this energy that's been deposited. So this is basically, this is a particle-particle collision. The kinematics can be solved rather quickly, in the sense that this type of events are discussed in. I see you are perplexed.
I read it a few days ago. I just don't remember enough about it to add anything.
I see.
But it was a WIMP particle that they detected a sign through, or a signal.
No. The interesting part. Let's see what type of images come out. Yeah. So this is the figure I was looking for. So this is your dark matter particle.
Right.
It's part of the cosmic dark matter. So it surrounds all of us.
Right. So this is the kind of dark matter that has been thought of before, and it, like when you talk about a halo, it exists kind of like outside, mostly outside of the disk of our galaxy, and every once in a while we get particles coming through it. Is that right?
It's also around us. There is a population of dark matter in our solar system, around our solar system.
Okay.
And this is what we look for. We exploit this ambient dark matter.
Right.
That strikes a nucleus. So this is the WIMP. Strikes a nucleus, leaves some recoil energy, and we look for this recoil energy, basically.
Right. And it's
what they saw in xenon. This is a different detector because it's germanium. If you xenon, like in the Gran Sasso experiment, they don't see an excess of this type, but they see an excess of particles, possibly of particles scattering off electrons. So it's that's why it's in the it's at a different energy.
So instead of seeing what they expected, they saw something else. And this other thing that they saw points more towards axions?
Well, you cannot have an... Okay, it could be an axion if you didn't have the stellar bounds that I was telling you before.
Gotcha.
So if it were an axion, it would be coupling too strong to the photon.
Gotcha. Okay.
And the electron. So the QCD axion, the axion solution is shut off because of this.
Right. Okay.
Unless come up with some mechanism or some ideas why. So there is a strong tension between what they see and the stellar bounds. It's not easy to come up with if you really insist on axion interpretation.
Okay.
The interesting part about this is that these type of experiments, so they're actually this xenon experiment in the Gran Sasso, and they are about to upgrade it. So they will go from xenon 1 ton to xenon n ton, which will, I think, quadruple the amount of scatterers, the amount of they will add a factor of few to the amount of xenon that they use.
Uh-huh.
So they will have a better sensitivity, and this will allow to discern between is this background, is this a new signal.
Gotcha.
As soon as they get back online. But they also have competitors. They have there are other 2 experiments at least that are in the same process. They will have a similar target, similar mass target, and similar timeline. So this is really a race. Very exciting. Nice to see what will come up.
Yeah, it's interesting seeing how that's going to play out.
Mm-hmm.
I do have there is a question that's pertaining to this, what you're talking about now, is somebody has read an article and they say that a solar axion was detected, and he's asking how is that different than a dark matter axion? And I think you kind of explained that, but could you go over it just?
Not really. I didn't go into solar axions, but basically, if these particles exist, they can also be produced in stellar processes, like for example in our sun, but not necessarily be dark matter.
Right.
In any case, you have to transcend from the fact that they're dark matter, the production. In any case, the coupling is that they see that they require in this xenon experiment is in tension with what we have from stellar bounds. So you can explain in terms of dark matter axion-like particles. You can explain in terms of solar, but with a coupling that's already been excluded by other experiments.
Okay.
So in any case, even in the solar axion interpretation, and in the paper of xenon, they actually have both dark matter and solar axion interpretation. But in any case, the coupling is from the stellar bounds excludes both these possibilities.
Right.
Yeah. So just a quick update. So these horizontal lines here look for axions that are produced in the sun. So these are basically sort of telescopes with a magnet at the end of it. They look directly in the sun and look for axions that are produced in the sun. So the advantage of this technique is that you don't need the extra assumption that the axions are the dark matter. They could just be a particle that doesn't have the right energy density to be the dark matter, but it's there and it solves the strong CP problem, and it's also produced in the sun. So these experiments in this region here serve for this purpose.
Right.
They are called helioscope.
And so that would be like one of the cousin axions like you were talking about earlier, right? The one that isn't a dark matter component,
well,
but
in the yellow region is really the QCD axion. When you step out of this yellow region, it's one of the cousin axions.
Okay.
If it's here, it's axion particle. Yeah.
Okay. So I kind of want to have you talk over a little bit about the little halos of axions that could exist, and potentially the axion stars that you've looked at. Mm-hmm. So I think some people would be interested in those two things, because for me, when I saw you were talking about the axion mini clusters, I was like, oh, this would be a cool episode for a Star Trek thing. So what would happen if the Enterprise came up to an Axion mini cluster? Like what kind of things would go on? You know, like what did they see and stuff? So I think it'd be kind of interesting if you went over that.
So yeah, Axion mini cluster is a clump of axions of a mass of the order of an asteroid, but it's spread out a much larger volume, roughly corresponds to the astronomical distance, Earth to Sun distance. So mass is ordered 10 to the minus 10, 10 to the minus 12 solar masses, or 10 to the 20, 23 grams, over a volume which is 1 AU cube. Such an energy density stored, so this is extremely frothy object, no?
Right.
But still, it's around 1,000,000 times more dense than the ambient dark matter density.
And so
this gives you the idea of how sparse dark matter is.
Yeah. So if like the solar system, our solar system, were to kind of like plow through one of these, would we, if we were able to detect these kinds of axions effectively, would we see kind of like an increase of that kind of that? And so it would be like, oh, okay, cool. Then we actually do know that Axion mini clusters do exist.
Yeah, so in this plot that I was showing before, if Earth really flew through one of these structures, since these experiments are sensitive to the local ambient density, going through an Axion mini cluster would basically trigger these experiments because the sensitivity is dependent on the density. The higher the local density of dark matter, the further the more they can probe. So it would be relatively easy for these experiments to probe the dark matter interpretation here, but they have to be tuned. Remember that these are cavity experiments.
Right.
You need to fine-tune them to the right frequency. This is why people have started to speak about multiply tunable cavities, so that if you happen to be in one of these events, you are in the right channel in some of these cavities, so that you can detect, you don't miss it.
Right. So there's a question that popped up real quick. So would Axion mini clusters give off visible light? And initially I kind of had a thought, like, if our sun and our Earth were, our magnetic fields were tuned just to the right era, would we potentially catch glimpses of photons flying out from the mini clusters? But you can answer that however you'd like.
Well, you need this diagram here, axion photon. This is what I'm working with people in Amsterdam. So remember axion photon, and what we are looking for is Axion mini cluster. These are the guys. I will tell about them shortly. Axion mini cluster and neutron star. Where is it? Here. So let's take a neutron star. A neutron star has a magnetic field around it. So the idea is to exploit the magnetic field of a neutron star. And you have axion photon conversion in the magnetosphere. Basically, this happens when the plasma frequency is of the order of the axion mass. So everything is sort of self-consistent in this type of models. You can You have a spinning neutron star. You have a dipole magnetic field, and you can also infer the amount of charge, ions or electrons that are around this neutron star. So you can basically map the plasma frequency around them. Now, when an Axion mini cluster flies through one of these objects, you sort of have a cavity experiment, where the magnetic field is not the cavity field, but is provided by the neutron star.
Right.
So what we look for is for this type of event, like magnetic field of a neutron star, and axion provided by the Axion mini cluster, that convert the axions inside the mini cluster into a radio frequency. This has been done already for cosmic dark matter. This is why here I thank Pensati, University of Michigan, for some speech he had on the argument, and he already worked on this type of ideas for dark matter axions. So you have dark matter axions that fall into a neutron star and emit radio waves. We are in the process of doing this for Axion mini cluster. What does it mean we? I just want to briefly mention who are we. Thomas Edwards now is with Catherine Fries in Stockholm. Bradley is now in Spain. He's extremely good, working on primordial black hole. Christoph Benniger is my current supervisor, and he works on everything. And he's very interested in machine learning nowadays. And this type of project that we're doing basically maps the type of, so we get a bit more into astronomy, maps the type of events which should be in a ring-like shape in the Milky Way. And we're also trying to predict the flux in micro-Yankee of the event, and how long such an encounter would last.
So that's kind of an interesting map. So where would the galactic plane lie? Where's the core, and how far out would you expect the arms to be? Just to give people an idea of where this actually would sit, if it was in our galaxy.
Well, the sun is 8.3 kiloparsec away from the galactic center. And most of these events, according to what we find, should occur within 4 kiloparsec. So half the sun galactic center distance, halfway between us and the galactic center.
So that's cool. So we could potentially see it.
Just mention this. Okay, so this is the galactocentric distance. Okay, we are here. So this is 10 kiloparsec, and the sun is at 8.3 kiloparsec here. What we plot here is the survival probability of Axion mini clusters. So if Axion mini clusters get too close to a star, they are disrupted. They're ripped apart because they're too fluffy.
Right.
So what we're doing, what part of this work was also trying to understand how many of these Axion mini clusters are there. So we have done some numerical computation that basically showed us that within 1 kiloparsec, nothing has survived. So we don't have this type of fluffy structures anymore.
And there's just because there's
zero.
Yeah, there's just way too many stars near the core.
Exactly.
So it's just like anything, it rips anything apart.
Density of stars is too high, exactly. And then according to different models, how differently we model the orbits of the Axion cluster and their profile, how they look like. We have different models for how many of them are there around us.
Right.
The important part is that even in the most pessimistic scenario, we still have around 30% of them that have survived around us. So there should be a meaningful number of events that we should see from them.
Cool. Can you tell us a little bit about the Axion stars?
Yeah, remember that in everything I said, this word here is key.
Right.
It's all preliminary. So, although we are a sort of advanced status.
Yeah, I thought they were really cool too. I had never come across those kind of things, and so I think other people would also be pretty interested in hearing about that kind of stuff. Just because it's so new, it's like, oh, this is like completely new stuff. Nobody's heard of it yet.
It's a new field, so basically the idea is if you want to take seriously a theory like axions, you need to consider all of the outcomes. Axion mini cluster are a sort of natural prediction
right.
theory, which means that you almost inevitably form them in some cosmologies. And this comes with a lot of other aspects, like the ones we are studying. So this is a way, basically, to disprove or find the axion through indirect methods, as opposed to the laboratory searches. It's a sort of new branch, if you think of this, because then you need to go talk to other astronomers and actually do this type of searches. If you find something, this needs to be confirmed in laboratory as well by this type of experiments, the cavity experiments, the detection. But everything has to match. So if two experiments see the same thing, then this strengthens the case for the existence of these particles. So this is the spirit in which this type of research is going.
Yeah, well, it's really cool. It's
this is the thing.
Very interesting.
You need to think of the which radio telescope could do the trick.
Right.
Axion stars. So this is really cool because it has to deal with condensates.
Yeah, like a Bose-Einstein condensate, right?
Exactly. So basically, it's possible that in the inner parts of the Axion mini cluster, where the density is higher, the axions, which are bosons, lose energy, so much energy that they get into the lowest possible state, and they form a condensate. So now they start to behave as waves rather than particles. Speaking about what we discussed earlier. Now you have to think of axions as waves. And you know there is Heisenberg uncertainty principle.
Right. So that's just you don't have an idea of the momentum if you have an idea of the position, and vice versa. If you know.
Yeah. So if you say that these objects collapse into what is called a star in the sense of hydrostatic equilibrium, but also in the sense of an object of a finite radius, r. Or if I move you, well, you know that the axion is confined within this radius. Because of the uncertainty principle, you know that it has some momentum. This is the formula for the uncertainty principle. The positions times the momentum, which is at the denominator, is of order h bar, which is a constant. So basically, if you want an object of some radius r, you know the velocity at which these objects are moving inside the star. I call it a star because basically the hydrostatic, because the uncertainty principle gives these axions some velocity, as I said, which is a form of pressure in a star. And you have to counterbalance this pressure if you want to have a stable object.
Right.
What counterbalances it? Gravity. So here in the self-energy of this axion star, you can write a first term, which is a pressure term, basically, which is given by the total mass of the axion star times the velocity squared, associated to the Heisenberg principle, and self-gravity term. Neglect the self-interaction term, just the pressure and gravity. Pressure wants to break apart the star, gravity wants to pull it together. So this is an axion star. It's star not in the sense that it shines, but in the sense that it's an object in hydrostatic equilibrium between gravity and pressure, which is provided by this quantum pressure.
Do you have an idea of what mass you would have to have in order to create this situation? Like how much axion mass do you have to have in order to create that equilibrium? Do you have an idea for that?
I have an upper and lower limit, which is a lot. No, in this type of theories, like how big is an axion star, we don't know.
Right.
So basically, the mass and the radius are related by the fact that we want the equilibrium of the star.
Mm-hmm.
So if you impose hydrostatic equilibrium, you find that the radius is inversely proportional to the mass. But you don't know how big this object is, you don't know how massive it is. Let me go to the next slide. So these are my collaborators for this project. Katie Fries, who now is in Austin. He used to be in Michigan. And she's also in Stockholm. Sebastian Baum now is in Stanford. Javier Redondo is a fantastic guy in Zaragoza. Frank Wilczek, MIT, Arizona, Shanghai, and Stockholm. So here I have put the radius of the axion star. Unfortunately, I used these rescaled units of 1/mass because we wanted to be more universal. But this is sort of radius in some units, arbitrary units. And this is the mass in some units. You have to look only at this blue line here, which is what you expect for the QCD axion, that matter. So everything else, I would skip it, but look at this blue line. This is what I was saying. The radius is inversely proportional to the mass. So the bigger the mass, the more compact the object becomes. Now, if the object becomes too big, it also becomes so dilute, so the density becomes so low that it gets easily stripped out. And this gives a lower bound on the mass of the axion star, which is of the order of 10 to the minus 17 solar masses. In grams, this is 10 to the 16 grams, I think. The upper bound is given by this scheme, which is given by the fact axions will start to interact with themselves and destabilize the star. And this occurs at around 10 to the 22 grams. So you go from 10 to the 16 to 10 to the 22 grams of this object. Similar as the Axion mini cluster, basically.
Gotcha.
Few order of magnitude less in mass. Well, there is a lot to do about this. So the question is, if the Axion mini cluster really exists, how do you form these Axion stars? This is already like kind of understood, but does each of the Axion cluster host an Axion star? How can we exploit their existence? So what can we do with these objects? How can we use them to detect them, to prove that they actually exist? So, see, new fields.
A lot of new work to be done. So,
yeah,
the
simulations of these are at the preliminary stages.
Yeah. So there was that one last thing I wanted to probe about, and that's how you're relating axions to gravitational waves. Just because we had a couple talks about gravitational waves a few weeks ago, and I think it would be interesting to loop that back and see, these could be potentially related.
Well, yes, you can. Yes. So my original idea for this project was to exploit this branch here, in which the Axion star becomes so dense. This is a new equilibrium. It has nothing to do with what I discussed before, but it's a possible equilibrium for Axion stars. So, in which they have some mass and some radius associated with it. In this equilibrium, the Axion star would be so dense that actually binaries would form would be observable in gravitational waves.
Okay.
The point is that in this work we show that this branch doesn't exist. This is why it's dashed. So basically, yeah, that's it. No dense Axion stars, as they wrote.
Okay.
So no gravitational waves from this object. But nothing prevents us from, I don't know if I have it, yes. Nothing prevents us from stepping away from using bosons instead of axions. So other types of, or more general types of bosons. You can do the same trick as you did to axion for general bosons. So a hypothetical particle, new hypothetical particles, which could form boson stars instead of axion stars with the same physics as before, more or less, and be in binaries that can be potentially detectable in gravitational waves.
That's cool.
So basically, a boson of this type is less motivated because it's not related to solution of the strong CP problem. It's not directly tied to the standard model. Still, it can exist, and one way to probe this is by gravitational waves from binaries. Other ways in which you can relate axions and gravitational waves, I would say mostly the cosmology. So the way in which you want your cosmology or as a scenario in which your axion physics takes place, can also be a cosmology in which you have some gravitational waves, primordial gravitational waves that are formed because of some phase transitions or because of some features that are required in your framework for your axion theory to work. So not indirectly related to axions, but still present. So what else? I know that yeah, basically this is my short answer about the relationship
That's fine.
pulsars and waves.
Okay, so we're moving on to close to 2 hours, so it's been a while. But if you don't have anything else that you want to talk about like directly, there's a bunch of questions. If you want to take some of those and then call it good for there, if you're okay with that.
Sure.
Okay, so some of these go back to what we were talking about a while ago. So Kurt asks, is the axion a particle that causes the sheet to oscillate, or is it a property of the field? And so we kind of answered that, and it's the particle is part of the field, right? And so it's yeah, go ahead.
You finished bit. I didn't. Can you repeat?
He asked, is the axion a particle that causes the sheet to oscillate, or the field to oscillate, or is it a property of the field?
Okay, so a quantum is an excitation over the background. So it's a property of the field itself.
Right.
Say.
Okay.
Once you study at the quantum level.
Right. So I don't know if
it's a property of the theory when you go from classical description to quantum description.
Right. Okay. So I don't know if you can answer this one, but he asks, so the universe is made of an underlying quantum foam, and all the particles are just expressions of waves inside the cosmic foam? Question mark.
The point is that I don't treat this type of... okay, so foam is one theory has been put forward to explain how can we blend quantum field theory and general relativity. So this idea that I was telling you like an hour ago about the fact that we don't know how to marry these two realms, particles and general relativity. One way is to consider space-time, but I don't work on this, so
yeah,
I don't have a proper answer on this.
Oh, that's fine.
This is a way to quantize gravity.
Yeah, that's how I understood it too. So, like, foam is a way to understand the quantum nature of space and time as it relates to particles being inside of it, and like you said, pulling it together as a grand unified theory. So, but yeah, that's a difficult question to answer. So
especially 4 a.m.
Exactly. Yeah, it's really late for you. So he also asks, have WIMPs been detected? And I'm pretty sure the answer is no on that.
Yeah, there have been claims here and there, but they've always been refused at the end.
Right, nothing definitive.
You see excesses at like 95%. These are called like 2 sigma, 3 sigma. This is called the deviation, or how significant this signal is. But it could be a statistical fluctuation that occurs extremely rarely, still it occurs, or it could be something new. For WIMPs, it was always shown that it was just statistical fluctuation, because if you take more data, then the signal goes away.
Right.
It goes back to the within the fluctuation. So WIMPs have not been detected yet, unfortunately. This would have been a huge breakthrough.
It would have been. So he has another question. Do you personally think that the xenon has detected an axion, or do you think that it might just be some of that statistical background fluctuation that you're talking about?
It's not easy to explain this signal in terms of background, because this experiment has been going on for a while, for 15 years. Mm, Still, personally, I think it's something that will go away.
Yeah.
Maybe something new, but so it's good. It's same to look at other explanations, exotic explanations. Maybe it's really something new. I don't think so. I think it will go away today.
Right.
But it's nice. It's nice because it sets great, like, puts pressure between these different consortium, different experiments. Look for this. It's good for science. Good for science at this type of debate.
Yes, exactly. Okay, so this one's more of a personal question, and I'm sure we've pretty much answered it considering your upcoming position. But he asked, as your career continues, what experiments are you thinking about developing or participating in to detect the Axion?
Okay. I definitely want to continue working on this red astronomy part, which is basically just it has just started. It's seminar part.
Yeah.
So I would like to, with other people, to see if we can group over 20 people in the field and push for this Axion radio astronomy searches in a coordinated effort.
Right. That would be cool.
Yeah.
Maybe you'll be the one to discover it. That would be pretty awesome.
Who knows?
Yeah.
The point is that people have used existing data. You can also think about taking data specifically for this problem. So this is why, but for this you need, you know very well, you need observation time, you need to advocate for that clearly. Right. So yeah, this is basically what my main motivation for observations would be. Okay. I hope this answers.
Oh yeah, sounds good. Also, how many axions are thought to be in local space? Like, what would be the density? Are they like neutrinos? Are there billions flowing through our bodies right now? If they do exist, is that what do you imagine?
The mass is much more than neutrinos, I would say. If it is the dark matter, I remember a billion of trillion, like astronomical number. A number is extremely huge.
Gotcha.
A million billion axions per centimeter square per second.
Wow, that's a lot.
A million, yeah. 10 to the 15.
Interesting.
If they pick up the dark matter, which means that you fix the energy density, but given the axion theory, you also fix their mass within some benchmark.
Right.
So you know the number density from that.
Okay. There's another question here. This one I could answer just really quick. What's the difference between dark matter and a black hole? They are different things. Black holes are the accumulation of tons of matter into a single spot, often caused by the death of a large star. So you're taking real matter, which is the stuff that we are all made of, and compressing it down into a single point. Whereas dark matter is something that is completely different than the matter we're made up of, and only interacts. Some ways it's gravitationally only. Some ways it's very weakly interacting in other ways. It just depends on the type of dark matter. But they are very different. But I don't know. Does that preclude throw away the possibility of a black hole made completely of axions or dark matter? Don't know.
So I would say that I have two things to say. One about black hole. Okay, just to basically, it could be that some of the dark matter is in black holes.
Right.
This was big question mark and 80s. Basically, now we have lensing. So the idea is that if you look, for example, at a target galaxy, or if you look at the galactic center bulge, if you have a black hole of some mass that flies around, between you and what you observe, it would make a lensing event, a transient lensing event. Based on this type of observation, we can place bounds on how much mass is in black holes.
Right.
So we now know that dark matter is not in black holes, except excluding some window that is around the asteroid mass black hole window, which means that it could be that dark matter is in the form of asteroid mass black holes.
Right. So you're saying that in order for black holes to be the explanation for dark matter, they would have to be very small black holes with the same mass as an asteroid?
Yeah.
Gotcha.
Yeah, exactly.
But
it's around 10 to the minus 11 to 10 to the minus 15 solar masses. That window is still open.
Right.
Roughly. And in other mass windows, it might not be 100% like the totality of the dark matter, but it could be a fraction of it, 1%, 0.1%.
Right.
Yeah, black holes could be a fraction of, especially those of primordial origin. So those are not formed by astrophysics, but by much earlier.
Yeah, from the beginning of just after the Big Bang. Right.
Another thing I want to say about dark matter is that we know that it exists from gravity. You were saying it interacts gravitationally. Exactly, and that's
right.
How we know it exists.
Yeah, because that was the precursor for it actually coming into existence. You know, like the rotation rates of galaxies not matching what they should be. Like things like the bullet cluster, where you have gases going through each other, and different effects of what's going on. And even just in galaxy clusters, how the galaxy clusters themselves are moving. Makes us believe that there is something there that we're not seeing. So, yeah, it definitely exists, but we're just not sure what it is. And like your research, axions and stuff, are trying to figure out if that is one of the things for it.
Yeah, everything you said is correct, but it's only gravity.
Right.
They are all gravitational hints.
Right.
They are very strong hints because they come from different length scales. And they can all be solved by one assumption. We have dark matter.
Right.
That's why it's so powerful, and that's why people believe in this. The interaction of dark matter with ordinary matter is basically what would give us the next step.
Yeah.
What would tell us about the particle, if it's a particle.
Yeah.
If it's not a black hole, which could be in this mass window that's still open. So yeah, I hope we answered the person.
Yeah, I think we might have answered too much, but it's okay. One last question, and I think we're good.
Okay.
So Kurt asks, were the mini clusters created shortly after the Big Bang, and then they've been floating around forever since, or could it be like generated by other processes, maybe accumulation of them over time, kind of like how galaxies are formed, maybe? So, what is your thoughts on that?
Yeah. In the scenarios we assume they're formed basically right after the Big Bang. Way before galaxies are formed.
Okay.
It could also be that primordial black holes, so black holes that have been there already from the very beginning of time, accumulate dark matter around them. So they are a strong gravitational field, and it doesn't mean that they have to swallow all of the dark matter around them. The dark matter can just orbit around them.
Right.
So they could be black holes with an accumulation of dark matter access, for example, or other types of dark matter around them. This would also create clumps. Basically they are formed in the very early universe, and then they follow structure formation. So they undergo the same merging events as other larger structures. So basically, out of smaller building blocks that make up Axion cluster, you bring more and more of them together, and you form higher masses of this object.
Right.
Halos of Axion cluster.
Right. Okay, well, that's all the questions. Is there anything else you want to add into this before we take off?
I would like to say that I really enjoyed. I thank you for the invitation. It was great to be part of Salt Lake City and South Physics Observatory after so much time. I was really excited for this.
Yeah.
I have great memories from Utah, University of Utah, and Salt Lake City. It's great that I have some chance to talk about what I'm doing to new generations of students and physicists and people are interested in the field.
Well, I have to thank you a lot for being willing to do this, and also for sticking around for like twice as long as we expected to. But no, I enjoyed it a lot. I'm sure a lot of other people. Kurt does say, thank you for an interesting lecture. Thanks for staying up so late at your local time. He says, go get some sleep. Best regards for your future career. And he hopes to stumble onto a published paper in the future on axions with your name on it. I'm sure there are several out there already. And he says, apologies for not being bilingual and being able to listen in Italian. But I have that same problem. So, yeah.
Okay, I'm okay with it. I hope I made my point.
Yeah, no, you did really well. Everything was concise, and like I'm sure everybody understood it just perfectly. So, thanks again for doing this. You're always welcome to come back.
I would definitely love to meet in person when the situation allows for it.
For sure. Hey, we still have colloquia on campus, so maybe you can get you out to do one of those for the department again. So that way our department can see all of the cool stuff that you've been doing while you've been gone. So
in a year, I will.
Yeah, of course.
Provide it. Yes.
But
yeah. When the situation allows for traveling.
Oh yeah, for sure.
I would come for sure.
Yeah, that would be fun.
Yes.
That would be fun.
Yeah, I want to see how Salt Lake has become.
It's
almost 10 years.
Yeah, it's changed a lot since you've been here.
Yeah, that's what I heard. Yeah, I'm really curious.
Yeah.
So it's great already back then. I want to see how it is now.
Yeah.
Okay.
All right. Well, you have a good night. Thanks again for staying up so late, and I hope to talk to you soon again. So, have a good night.
Yeah.
See ya.
Thanks. Well, thanks. Thank you.
You're welcome.
Bye.
Thank you. Bye.